All right, so welcome everyone. Thanks again for joining us. Today in our Banach Space webinar, we have Kevin Beanland, and he will speak on closed ideals on Tsirelson and Schreier spaces, I think.
Yeah.
Go ahead, Kevin.
Well, looking at myself. Well, when I agreed to give this talk, I didn't anticipate there being such a excellent crowd here. I'm really happy that to see so many faces in the Banach space community to come to check out my talk, especially under these obviously very difficult circumstances. So I considered maybe trying to postpone my talk, but it's been good for me this week to think about some math and do the talk and outline the talk. So if anybody has any comments during the talk, please just interrupt me. If you try to wave or raise your hand, I might not see it. So you can just unmute yourself and say, excuse me, or something like that. And I'll be happy to stop and, take any questions. So this work that we're talking about today, can people see this? This is work with,
yeah,
hands a little shaky, with Niels and Tomasz. And this paper was submitted last summer. And it was a joint project that was going on for a few years before that. So, and we're going to be talking about, the title of the talk is the closed operator ideals on Schreier space and Tsirelson space. And so I have, I think it's fair to say I have a little bit more experience with Schreier space and Tsirelson space than Tomasz and Niels did, and they have considerably more experience with operator ideals and these types of questions than I did. So it was a natural question for us to study. It was a good way for me to introduce myself to the material, and hopefully they got something out of my collaboration as well. I did want to mention just at the beginning of the talk that that I recently learned that Boris Tsirelson died in late January. Probably everybody has heard that. He died at 69 years old. I unfortunately never got to meet him, but he was very influential in my career, and his papers are obviously hugely influential. And if you haven't gone onto his website and looked at some of his personality comes out in his writing and in his website, and some of the things he's done. I also found out that he edits Wikipedia pages. So unfortunately, like I said, I never got the chance to meet him, but so I guess I'll go ahead and dedicate this little talk to him, because I was very sad to hear that news. So I guess, again, I want to also thank Bunyamin for organizing the seminar. I was unfortunately unable to come to last week's talk, but I saw that it was a major breakthrough in the rebate program. So I'll try to follow it up and give you something else equally or somewhat interesting as well. So I've been planning this talk I've given some version of this talk to a non-Banach space specialist audience. So I had to update it a little bit, and partially also I had to update it because Bill and Gideon just posted a new paper on the archive of ideals of capital LP. So I think hopefully people have these questions on their mind about what are the ideals of various Banach spaces, and this will seem relevant to that. So the beginning of the talk, I think probably the talk is really just two parts. The first part, I'm going to give you guys history of these types of problems in the surrounding literature. So I know, for example, many of you know this surrounding literature, but if you don't, I think it's interesting. You can also read the papers, the beginning of the paper I have with Niels and Tomasz. We give a pretty decent historical background of these the problems of classifying closed two-sided ideals on a given Banach space. Also, Bill Johnson and Ian Sheckman and Joe Pizier, they have a paper the ideals of capital L1, and they give a pretty good background on the problem as well, these problems as well. And so let me sort of start with the what I'm going to get to is we're going to be looking at T is always going to be Tsirelson space. Okay. And the other spaces we're going to be looking at, let's call them X. This is terrible notation, but I'm going to go with it for now. X Sn. We could just call it Xn if you like. And this is the nth order Schreier space. And all of the results that are in the paper with Niels and Tomasz are on the operator ideals, the ideals on X, where X is either Tsirelson space of the nth order Schreier space. We're looking at the close, finding closed, two-sided ideals for this collection of operators. There's a kind of a good reason, which I'll get to later, why we are only considering these spaces right now. There's some really nice structure theory for these spaces about the complemented subspaces of these spaces. And in order to have any chance really of characterizing or classifying or really studying closed ideals of operators on a space, you're going to want to know what the complemented subspaces are, or you're going to want to know you're going to want to have some structure theorems about the complemented subspaces. Okay. So the first thing is, let me give you a little bit of a background on this. If X is either LP or C0 for any P within any range, then we know, excuse me, that's my notifications. So we know the closed two-sided ideals of B of X. That's only there's the trivial one, of course, and there's the compact operators of X, and then there's the whole thing of X. Although this isn't necessary to explain, I generally write L of X instead of B of X. So if I accidentally write L of X later, I'm writing B of X because Niels prefers B of X, and it's in the paper as B of X. So I'm happy to go with that. B of X. So these are the only ideals for LP or C0. This is a somewhat straightforward argument with modern tools in Banach space theory and blocks and these sorts of arguments. And but back in the 40s, when Kalkin proved this theorem for L2, it was a paper in the Annals. Later on, it was proved in 1960 for LP and C0 by Goldberg, Marcus, and Feldman. So there was some. So the timeline is the 1940s. It was proved for L2 by Kalkin. Of course, there was probably several other results in that paper as well. And for LP in the 1960s. By the way, I've tried to do as good a research as I can on the historical timeline of these things and included as many results as I can. But I know that I'll probably forget either a date or a person's contribution. I apologize in advance, and I'd be happy if you corrected me at the end. So there are also many non-separable versions of these results for non-separable Hilbert space. Hilbert space. They don't get exactly this result. You get a chain of ideals depending on the density character of the non-separable Hilbert space. The results of, I believe it's Dawes, who might be on this call right now, for C0 of gamma for various gamma. So there are non-separable results and there's separable results. I'm going to kind of stick to the separable case. So the first part is, excuse me. So there's two kind of questions that you can consider when you're looking at closed ideals of a given Banach space. The first is, well, maybe you have some chance of characterizing these closed ideals, okay? That you will know all the closed ideals. And the second is, well, if you don't believe you have any real chance of characterizing all the closed ideals, maybe you can at least count them, or you can tell me something about the number of maximal ideals of the given space. So, for example, so let's start talking about the spaces that we know how to characterize the closed ideals. Well, we have these right here, right? And then a big jump, 2011. I think this is I think it's in 2011. At least that's when it came out. This is the Argyros-Hayden space. Excuse me, Hayden space. Okay. XAH. And the operators on the Argyros-Hayden space are a multiple of the identity. So let's just write multiple of the identity plus compact operators. I think this paper now has over 100 citations, and it obviously solved many problems in the literature. It was the first example of a space where it was known that the operators are separable. The space of operators is separable, non-trivially invariant subspaces, lots of different, solved several outstanding problems in Banach space theory, and also gave operator ideals that were of this form as well, where you had K of X and B of X. So, you know, on one hand, you have L2, which has lots of symmetry and lots of different things going on, and it has this structure. And on the other hand, you have a very rigid Banach space, and the ideals have that structure as well. So, well, that's one other example. Let me give you another example is by Tarberd, who's a student of Richard Hayden, graduated, I think, in 2012. And he constructed a space. A space with lots of other properties. Has a strictly singular non-compact operator, and is of the form is a predual of L1, a script L infinity space, HI space. So that for each n bigger than 4, so that the ideals they're exactly n in linear order that have to do with the powers of a given strictly singular operator. And so we have exactly n in linear order for this non-separable, for the separable space. I should mention that I'm framing these in terms of I'm framing these results in terms of the consequences of the ideals, the closed ideals on the space. However, I mean, that's not really the reason why we care about these spaces. The other examples that we know are L2, the C0 sum of L2n. Okay. This is due to Laustsen. Let's get that extra S. Loy and Reed in 2000. 4. And the operator ideals are compact, call this X, compact, factor through C0, closure of the ideals that factor through C0. Okay. Of course, these are not equal to each other, and V of X. And those are exactly the 4 ideals that you have for that one. And also the dual X star has a decomposition that's very similar, except you replace C0 with L1. Okay. Okay, and there's some other pretty. There's one more paper. There's several other results related to this, but I just wanted to stop there. In terms of characterizing, we know all of the ideals on a given space. Right? Characterizing. So let me turn to capital LP. In capital LP, we've known for since the at least 1981. Right? So we're looking at B of capital LP 0, 1 for P between 1 and infinity. Okay. And since at least 1981, a paper of 1981, there's a paper of Bourgain, Rosenthal, and Sheckman. And 1981, the paper Bourgain, Rosenthal, and Sheckman, they produced omega 1 many non-separable, Aleph 1 many non-isomorphic, not non-separable, complemented subspaces. So with the idea that complemented subspaces produce, in some cases, that the complemented subspaces produce ideals, well, Peach observed in his book that you have also Aleph 1 many different ideals on B of LP 0, 1. And I do hope that Bill eventually speaks in the seminar at some point. I would love to hear him to give a talk, but I don't want to steal any of his new results here. I certainly wouldn't. But reading his paper, I learned that in 2000, his and Gideon, 2018. 2018, Schlumprecht and Zach proved that there's a continuum many on capital LP. So we move, I guess, up from Aleph 1 to the continuum. And the most recent paper is, and they proved this in a paper in which they proved several other things. And then a most recent paper in, I would call this 2020, and this is a preprint from last week. Was it last week? Let's go with last week. Last week, maybe 2 weeks ago. And they produced 2 to the 2 to the Aleph not many closed two-sided ideals. Okay. And that's exactly how many there are, right? There can't be more than that. There couldn't possibly be more than that. There's exactly that many. And this solved a problem that's 50 years old. Okay. Is that right? Is it 50? I guess 42 years old. Okay. So there's some interesting progress being made recently and being made about this. Also in this paper, I've been looking at this paper quite a bit. It looks to me that you can use this similar technique to produce this many ideals on the two convexification of Tsirelson space as well. I could be corrected, but it seems to me that you should be able to do that as well. An interesting thing about
That's right, Kevin.
Is that correct? Okay.
Yeah. There's a remark in there that more or less says that.
Okay, good. Yeah. I was when I read the condition for the you want to produce an operator with certain conditions. It seemed to me that you want to produce an operator with conditions so that are already satisfied by the unit vector basis of the convexification of Tsirelson space or something like that.
Yeah, no, that's right.
Oh, that's right. Okay.
Yeah, we didn't mention that because we put in the example about the L2 sum of LPNs where the p's go to 2 and the n's go to infinity at a right. But Tsirelson is immediate. That one we had to make some comments about.
Yeah. That was interesting. I spent a little bit of time in preparing this talk to see if there was a natural way of doing that on the original Tsirelson. Maybe you could adopt the method or something, but I wasn't able to see it. But anyway, there are some ideas, at least on a basic level, a very basic level. There's some ideas there, especially using disjoint families, almost disjoint families of this subsets of the natural numbers, which are used to produce lots of ideals that, of course, we're going to use later when I talk about the Tsirelson and Schreier examples. Okay, so one of the things that's interesting about capital LP is, and the operators on capital, operator ideals on capital LP is that they have there's a unique maximal ideal. Okay? I won't write it out, but there's this specific maximal ideal that's unique for the capital LP. So everything sort of is bottleneck. I'm sorry? Yeah, okay. There's some other examples as well. The B of LP plus LQ. A whole host of examples in all different ranges for P less than Q less than infinity. This is due to Schlumprecht and Jacques, and this is a major paper from a few years ago, solving a problem from Peach. I think everybody started reading Peach's book about 5 years ago looking for problems because a whole bunch of them have been solved in the last 5 years. And it's been interesting. A lot of different techniques as well. There's papers by Thomas and Andras, and then Dan got in the mix at some point. Dan's here somewhere. And then there was Sorokin and Wallace. And they, all sorts of different techniques to produce ideals on closed two-sided ideals on a B of LP plus LQ for different P and Q, and then also C0 and L1 and different sides as well. Okay.
Kevin, I will do a shameless plug. LP plus LQ was started with Thomas, Vladimir, myself, and Nicole in 2003. So that's when we started working on it. So it wasn't 5 years ago. It was a little more than that.
This is exactly the type of comment I was expecting and hoping that somebody would make when I messed up a reference. So I appreciate that. So hold on, we got Tom Jack Jagerman. I'm not gonna, and Vladimir. I'm just gonna write Vladimir. And Thomas.
And
Thomas. Yeah. Okay. So you guys have been in this game a lot longer than I have, but I follow the most recent papers, and you have to go back and look at the paper trail to see who started this game. At any rate, so now you have the ball of LP, LQ. And then before I move on to Tsirelson space and Schreier space, I am just going to mention in 2019, it's Gideon and Bill take care of capital L1, 0, 1. Gideon, Bill, and Joe Pizier, 0, 1, C of 0, 1, and L infinity. What the heck is that? L infinity. I guess you could say 0, 1, just little L infinity. And they show that it has, each of these guys have continuum many ideals, closed two-sided. Okay, and you really need to either, usually, like I said, in order to have any chance at saying anything about the ideals, you need to have a pretty good structure theory for this closed, for the complemented subspaces. But also you usually need to say quite a bit more. And they certainly say more in these papers. And this paper is to appear in Math and Algebra. I just found that out. Okay, so I want to talk about Tsirelson and, again, Tsirelson and Schreier, which let's call that XN instead of XSN. Okay. And I'm going to essentially state the result and explain it as best I can. I'm not going to go through the proof, but hopefully the proof is well written. With Niels and Tomasz as co-authors, it has a much better chance of being well written. So I think it's something that you could look at and understand pretty well. But let me go ahead and see how we approached finding the closed operator ideals for Tsirelson and Schreier. We more or less, I think it's more or less arrive at the same results for Tsirelson and for the Schreier spaces of order n. Okay. And there's reason to believe that you could arrive at similar results in more complicated spaces, mixed Tsirelson spaces, higher order Schreier spaces, and these sorts of things. I don't see, there's an obvious theorem that you would need to prove in order to, it's not an obvious theorem, there's some natural theorem that you would need to prove in order to kind of make the first step. Mm-hmm. So let me just state some background here. So, so let's let X be either Tsirelson or Schreier, and it's the closed linear span of En and a natural number, right? So this is the unit vector basis, if you will. And for M, an infinite subsequence of the natural numbers, okay, or L maybe, would be both the same, infinite subsequence of the natural numbers. I'm going to say X M, okay, is equal to the closed linear span En N in M, and of course the same thing for XL, okay. The usual thing there. So these are, of course, subspaces generated by subsequences. And let's look at the projection, PM. This is the projection onto XM, the natural projection of the coordinates. Okay. Now, a natural collection of ideals to consider are the ideals generated by PM, and the closure of the ideals generated by PM. It's a completely natural situation. And in the case of Tsirelson and Schreier spaces, the space is very, very far from having a spread. It does not have a spreading basis, to say the least. So you can pick subsequences that grow very fast according to some condition, or so that the space xm in either case is not isomorphic to the space, the original space. And as a result, the ideal generated by the projection is going to be a closed ideal generated by the projection is going to be a proper ideal. That is a non-trivial proper ideal. Okay? So there's sort of the first time through thinking about this problem, there's a natural way to construct a chain of these ideals. But let me stop for a second here. Let's call this PM. The notation here, PM is the ideal generated by the projection, which we'll write like this: AI PM, BI, I equals 1 to n. And the BIs and the AIs are in your B of x. Okay. This is the ideal generated by PM. Hold on. Oh, good. Okay. And then, of course, we're going to take the closure. And from our notation, we're going to call these spatial ideals. And in this work with Niels and Tomasz, we exclusively use spatial ideals to study the structure of the ideals on Tsirelson or Schreier. It turns out that just using these very easy ideals, you can discover a lot of different structure within the lattice of ideals on these spaces, and a surprising amount of structure. And also it generates new problems. What else might be out there? So let's see. So we'll call these spatial ideals. And we'll say it's non-trivial spatial ideal if it's bigger than the compact operators, PM, and less than all the operators. Okay. So you've somehow picked a sequence that's spread down far enough so that the space it generates is not the whole space, and yet you've taken an infinite subsequence, so it's not the compact operators. Okay, okay, so let me state the results here. Okay. And this applies for x equaling, again, C or x Sn. Right? Okay, so there's a couple of items I want to go through, and I'm going to describe each of the items. There's just 3 items, and I'll describe there are 3 items in the main statement of the theorem, and I'll describe what's easy, what's hard, or what's reasonably hard, I guess, in each of the items, and walk you through it here. So, but some of the items imply the other ones, but it kind of builds up a little bit here. So the first thing is that the spatial ideals, non-trivial, okay, contain no maximal or minimum elements. Okay. Let's see what that means. I mean, if you take P of n, let's say this is your non-trivial spatial ideal, and you're looking at B of x and K of x. So if there's no if there's no minimum element, it means that I can find something in here. Well, that's pretty easy. right? Find something in there is pretty easy. You just take whatever sequence you have and you keep you sort of take a further enough lacunary enough subsequence so that it's not isomorphic to the original. It's not isomorphic to the original space, and therefore will generate a different ideal. So this is pretty easy. This means minimal. Okay, and maximal is a little bit different. You want to, any ideal that you start with, a spatial ideal that you start with that's non-trivial, okay? You can, I call this this is the fattening. So you can take your sequence, right? And you can fatten up the sequence enough so that you escape from being that the ideal generated by that new sequence is no longer isomorphic to the original ideal, but is still not isomorphic to the entire space. Okay, so you can take a subsequence to get something that's smaller, and you can sort of fatten it up, the subsequence up enough so that you get something bigger, right? No matter where you are. Okay, this isn't too hard, but in order to do this, you need some precise. You need to be able to quantify exactly when a subsequence will generate a space that is isomorphic to Tsirelson space and or Schreier space of order n. And probably Bill is thinking he knows how to do that because he wrote a paper on that 30 years ago. But there's a quantified way of saying when exactly a subsequence is going to be isomorphic to the whole space and when it's going to be not isomorphic, or when it's going to be isomorphic to the previous thing. Okay, so that's the first one, is that it has no minimal and maximal elements. That's just the first takeaway. As a result, these ideals can't be maximal ideals, right? Because you can always take a step up. None of these spatial ideals can be maximal ideals because you can always take one step up.
Kevin,
yeah.
So if I understood you correctly, you're saying there is no minimal ideal bigger than the compacts, or?
There's no spatial ideal.
No spatial minimal ideal. And this is because of Ackermann of Ackermann of Ackermann or something.
That's right. Yeah.
Okay.
Yeah.
Okay. So that.
Ackermann.
Yeah.
In Tsirelson, you do have to do Ackermann, right? I mean.
But then you take Ackermann of Ackermann of Ackermann. You can do this as much.
And then you do one more Ackermann, and you can. Yeah, that's right.
Yes,
yeah.
Okay. I got you.
Yeah. So the minimal's not so bad. The maximal, you're kind of imagine that you've moved far enough away. You've taken a subsequence so that you're not isomorphic to Tsirelson, and you want to fatten that subsequence up a little bit so that somehow you're still not isomorphic to Tsirelson, but you've moved away from the original subsequence as well, right? So that's the more difficult point. Okay.
Do you get, Kevin, this entire chain of spatial ideals, like maybe 20 many? I don't know how many you're getting.
That's item. That's item 2. When you mean you're doing great.
Oh, okay. All right. Sorry. Okay, go ahead.
Right. Yeah. That's right. That's exactly right. So as soon as you realize you can go up 1, right, you probably have a lot in between, right? Because you're fattening subsequences. So item 2 is this. Very good. Okay. Is this, if you have a spatial ideal, I don't really know the best way of, I don't know the best way of drawing this, so I'm going to draw it like this, which is a little strange. So you take a spatial ideal P, let's call it PL, the closure, I guess. And then you have another spatial ideal, which is properly contained in it, PM, or it properly contains. And this, you can make this proper or not with B of X. It doesn't matter. It can be the PM could be B of X or it could be not B of X. But I just care that PL is not PM. Okay. And in between any of these two, you get the following situation. I'm going to draw it like a block because I want you to visualize it as a continuum, right? Okay. Okay. So you have these chains that go through. So at each point here on this continuum, you have a chain that goes through like that. Okay, and then of course you have another chain that goes through like that. Right. So at each point of the continuum, you have a chain, and this thing denotes a continuum, a chain. Sorry, a continuum chain. How should I say that? A continuum many spatial ideals in a chain, right? Okay. So along each line, I have continuum many spatial ideals in a chain. So this point right here represents a spatial ideal, and this point right here represents another spatial ideal, where the inclusion goes this way, right? And they're all proper with respect to inclusion, right? So I go from PL to PN, I've got a continuum chain, and then along the way, they're all included within each other, okay? But not only do I have a continuum chain, I have continuum many chains, okay? So there's also continuum many, let's write the word many correctly, chains. And the chains have the following property with respect to each other. You can really see how we're going to use almost disjoint families here. I mean, there's just no way around it. If you want to produce continually many things, they're sort of far apart from each other in some way. If you take something right here that's in this chain and something that right here that's in that chain, we'll call this this J, that ideal. It's a spatial ideal, so nothing. I could call it Pn or something. And let's call this M, right? So they're on different chains, okay? And then I look at the ideal generated by J plus M, okay? And then I close it up, okay? Then that actually gives you PM, okay? So not only, so the chains themselves are continuum, but when you look at two different chains and any two different elements from the chain, you generate the entire, the one at the top, okay? So it's a bit strange. So let me see what the consequence of this situation is. Consequently, there are at least continuum many, I guess, maximal ideals. Okay, there's continuum many maximal ideas because if you apply this picture for, oh, hello. If you apply this picture for those things being equal to each other, right? So then you have all of these chains from any point. You have these chains that go to different, these chains that go to B of X, then and no two of them can be in the same maximal ideal, okay? So there has to be continuum many maximal ideals, at least continuum many maximal ideals. Probably there's 2 to the 2 to the n, the 2 to the 2 to the alpha naught.
Can I interrupt you?
Say it again.
Can I interrupt you?
Yes, please.
In the previous picture, I didn't understand. The M was a subsequence or an ideal? That picture there.
M is maybe the worst notation I could have picked. The M is an ideal.
But then on the right side, this PM is an
That's why I said it was the worst notation. Sorry. Let's call this K. Oh, K is compact. What should I call this?
I.
Curly I.
Curly. See, I was thinking curly I, but then I got nervous that I could write two curly I's that look the same. All right, so let's call it curly I. Is that good? All right. Now I don't know what I just did. I just doubled my picture. And then curly I. Yeah. So that M and that M are unrelated. Let me see if I get my picture back. Anyway, it's like moved my picture a little bit and it got funny.
You can undo probably.
Okay, now I understand. Thank
Does
you.
it make sense? Yeah.
Thank you. Yes, thank you.
Thank you. Okay. Okay, so that's the consequences. We have this many maximal ideals. And this is true for Tsirelson and Schreier, higher order Schreier. Okay, so let me just, I got like a couple minutes, and this is not me at the end saying, let me tell you a little bit about the proof, because it wouldn't be worth telling you a little bit about the proof, but it is worth to tell you, it is important to tell you what the theorems are, that without these theorems, you have no chance, we have no chance to prove this result, right? And the theorems are this. So there's a result of Kasasa. Oh my God. Sorry, Kasasa. And I think it's Kasasa Short. Certainly in the book, I believe it's due to them, but I could be wrong. It says that if you want to know if Tm is isomorphic to Tn, you know what I mean by Tm and Tn? I mean that the Xn and Xm and T is the Tsirelson space. That's true exactly when the sequences En, N and M is equivalent to En, N and M, N, I guess, equivalent, okay? So of course, the backwards direction is trivial. It's the forward direction that's non-trivial, right? That if these two spaces are isomorphic, then their bases are equivalent. And this is a non-trivial, it's a theorem in the book of Kasasa Johnson. Okay? You need this equivalence. You need to go back and forth, because what you do inside the proof is you want to go between the spaces and the projections and back to the projections, and you want to be able to say that the equivalence of the bases line up exactly with when the complement subspaces are in fact isomorphic, which is exactly when those ideals generate different the same idea. The projections generate the same ideals. Okay, so you need to be able to go back and forth there. And the second thing, this is for C. The second thing is a result of Kasasa Johnson and Zafiri from 1984 in Israel Journal. And it is a precise condition on, I would say a quantified condition for when two sequences, En, N and M, is equivalent to En, N in N, I guess. Okay, so it's a condition on the natural numbers themselves, on the subsequences of natural numbers. So essentially, what the condition says, for example, I'll give you a for example. The condition says that if you take a subsequence of the natural numbers, M1, M2, M3, and you want to ask if EMI, I equals 1 to infinity, is actually equivalent to En, for Tsirelson space, of course. Their condition says that, as Thomas was saying earlier, it has to grow kind of like Ackermann, but it just has to have a subsequence that grows kind of like Ackermann. But forget about that, saying the word Ackermann. As long as there are big gaps there are increasingly large gaps between some mk and some mk plus 1. And the way that you measure how big the gap is you look at the identity operator between Tsirelson space and L1, and you want the norm of the identity operator to go off to infinity, okay? And so this was established in this paper in 1984. And they give another, also in that paper, they give a condition whereby you can compare two different subsequences and see if they are equivalent to each other or one dominates the other, this sort of thing, okay? So this is absolutely necessary requirement for the proof inside of that. So we did the Tsirelson space first. Once we saw this, these papers and put them together, then we saw another paper of Gasparis, Janis Gasparis, and Lung. And unfortunately, I don't know the year, 2000, maybe 2006 or something. 2006. And more or less, they proved the same thing for Schreier spaces, right here and right here. What they have is, they prove that for Schreier spaces of order n, you have this exact condition. And they give even more precise conditions that the subsequential spaces are isomorphic if and only if their bases are equivalent to each other. And this is not an easy theorem at all. And then they give a precise condition whereby you can check if subsequences are equivalent to one another. And it's a bit of a different condition, but I'll just say it if you're interested and can have studied these things. Essentially, a subsequence of Schreier will be equivalent to Schreier, just go with Schreier, if somehow it's spread out. Okay, you believe that it has to be spread out a certain amount, but you can quantify exactly how spread out it has to be. Essentially, there are, you can find in that subsequence a Schreier set. So M1, M2, M3, and so on and so forth is a Schreier set, right? But when you look at the indices on which it's supported, that is k many Schreier sets of natural numbers. And if you can do this for all k, then basically that original subsequence is not going to be equivalent to the basis of Schreier. Okay, so there's this kind of condition there. So we use this Gasparis-Lung condition as well to prove inside we deal with this condition in order to obtain the results that I explained earlier. So let me just state two questions and then I'll be done, right? The first is, well, one is kind of a very informal way. I mean, there's certainly other ideals on Tsirelson space, right? However, every infinite dimensional subspace of Tsirelson space has a complemented subspace that's isomorphic. That's a complement subspace that's isomorphic to this Tm for some m, right? So these live inside of every infinite dimensional subspace. Okay, so what are the other ideals of Tsirelson space? There's certainly some candidates out there. That's not true for Schreier space. For Schreier space, there are, well, I'm sorry, I should say the condition for Schreier space is different. In fact, inside this Gasparis-Lung, which is really, I'd say, a deep paper, it's a really nice paper, and a lot of really good structure results about Schreier space in there, finite order Schreier space. They show that there's a complemented subspace that's not equivalent to space generated by a subsequence. Okay, and so what are the other ideals that you can get out of these complemented subspaces? Another thing is what can you describe? And you, anybody, describe or explicitly the maximal ideals, any maximal ideal of B of t, or of course B of x Sn. Okay, we know that the maximal ideals cannot be spatial ideals. And they contain this sort of chains of spatial ideals going off, you know, fattening and fattening and fattening. So I don't know, maybe there's an easy answer.
Question, Kevin?
Mm-hmm.
Do you know that they exist, the maximal ideals?
Yeah, I guess Zorn's lemma gives you the maximal ideal. Is that?
Well, yeah. Okay. Okay.
Maybe is that right? Is that? So you should always, every ideal should be contained in some maximal ideal.
Well, but I'm not sure.
Or the spatial ideals. So we know we have these.
The spatial ideals, yes, but.
So these spatial ideals should be contained in, but they have to be contained in different maximal ideals. Well, some of them. There have to be uncountably many.
But there could be a chain without maximal element, without upper bound, right? Couldn't it be? Couldn't you imagine a chain of ideals which doesn't have an upper bound, other than, of course, all of E of X, right?
Thomas, the union of a chain of ideals is a proper ideal.
Okay.
So is the closure.
Yes, okay, yes, Bill is right.
So is
the closure.
The analytic fact is just that the closure of a proper ideal is a proper ideal because the invertible elements are open.
Oh, I see. Okay, good. Yeah,
that's why that's why you get a maximal closed ideal.
Oh, okay.
Because a maximal ideal in the algebraic sense is automatically closed.
Oh, okay, yeah.
Thank you. Then.
All right, so thank you very much, Kevin. So officially taking the questions now. Go ahead, please.
Is Spiros on here?
So, someone was asking a question, I interrupted. Go ahead, whoever it was. Are there any questions for Kevin?
Any questions? Mm-hmm.
Nice talk.
Oh, thanks.
So the structure, the picture is you have continuum anti-chain and also continuum chain, like increasing chain, right? Yeah. Is that also continuum decreasing chain? Like what is?
Yes, it would be, right?
Well,
you have a bunch of, in between each of these, you have these increasing, decreasing. Unless I'm misunderstanding. Because it's a funny thing, you zoom in on the picture, it all looks the same, right? In between any two fixed ones, you have these blocks, right? And then you zoom in on any picture, and it looks like that.
You actually mean that the ordering on chains is isomorphic to the ordering on R, right?
Yeah.
The chains are isomorphic to R.
Yeah.
Okay.
So Kevin, to clarify something you said earlier, for T2, you get a 2 to the continuum ideals, but in T, you're not sure about that yet. Say it doesn't transfer over. It's the basically.
Well, no, we don't know. We don't know, if I may.
We don't know. I mean, your condition, you guys' condition as factoring through Hilbert space. Maybe you want to factor through L1 or something. You know, I don't know what the right way to modify it is. Probably, I mean, it looks reasonable that you could try something to change that condition a little bit, but I don't know.
So this situation on Schnupper space will be different, right? So because of minimality,
right?
So what are the spatial ideals? How many are there on Schnupper space?
Schnupper space has a shredding.
Oh yeah, you're right. So it's spreading basis. Yeah. Okay. All right. It's very different.
I mean, I should emphasize again that these structure theorems about Tsirelson and finite order Schreier, these are hard theorems. You know, if you want to know if subspaces are equivalent, if and only if subspaces are isomorphic, if only these are hard. That's a hard theorem, and also the kind of quantitative estimates on when sequences are equivalent. Those are hard theorems too. So you need those, and I feel good that I put this stuff to use. You know, we we put this stuff to use, you know, in troubling times here.
All right, thanks so much. Any other questions?
You have these continuum chains in your picture, and they're all spatial ideals associated with subsets L and M and so on. Within the chain, what's the relationship between the L's and the M's that you find in the same chain?
Okay. The LO that you find in the same chain.
Yeah.
I think they're just subsequence. One's a subsequence of the other as you go up, right?
And so,
or you go down.
Because, yeah. And so, because they're sort of you've got uncountable. You know, they're uncountable. So it's probably almost containment or something.
Yeah, it's either almost containment or it must be almost containment, right? Yeah.
But,
so
there is an issue. You know, there's an issue about how long these things can be, and there are funny cardinals. You know, there's B and there's T, and I've forgotten what all the other ones were called. But you know, the tower number, the tower cardinal T. Can you really, without extra axioms, get a continuum chain like this?
Well, I guess what we have is we're using almost just, so the original split, like at the beginning, is almost just joint families, right?
That's the split on the left-hand side of your picture.
Yeah. That's almost just joint families, which give you these kind of way of going out, and then you can sort of build up.
But within the same chain, I think, if I understand the question, right? So how do you go up? So there's a set theoretical issues in terms of.
No, there's. I think. I think there's not.
No.
No, I think, if I remember well, long time ago in my PhD thesis, I had a similar problem, and you can actually make them C long without any set theoretical axiom.
Yeah.
But maybe I'm wrong, but it sounds a little bit like a problem I had once. And
I think that the point is that the chains are not well-founded. This cardinal problem only comes for well-founded chains. Here we have a chain which is equal to R. You just have to take elements in between two elements.
Ah, right. Yes. All right. Right. That's yes. So it's a continuum, not a well-ordered.
Not a well-founded continuum.
Yeah. C. Okay. Yes. Okay.
Not indexed by C. Yeah.
Yes. Yes. Well, yes, because you keep filling the gaps. Sure. Thank you.
Okay, thank you. Any others? So if not, thank you so much, Kevin. So this officially finishes. I'm stopping the recording.
Let's give it.
Yeah, like a virtual clap. And now I'm opening the social hour. So